In part 2 of section 3, we're going to be discussing something called the difference quotient. And the difference quotient will be very similar to the average rate of change, but it is going to be a more generalized calculation for the average rate of change. It will eventually lead to a calculation of what's called instantaneous rate of change. Now, we won't actually get to do the instantaneous rate of change calculation here, but the purpose of this college algebra course is to get you prepared for the pre-cal and calculus sequence. So we are actually going to be starting to work on the material that's the background for the first branch of calculus that is studied in Calculus 1 called differential calculus. Hence the name difference quotient has differential built into it there. So you need to have example 7.2 handy. It says use the previous example and find the object's average speed. So we know average speed really means average rate of change between t equals a and t equals a plus h. So I'm going to go ahead and label these as T1 and T2. So that's going to make the average rate of change calculation a little more meaningful. So the average rate of change, which we know is going to be the change in y over the change in t, will be y2 minus y1 over t2 minus t1. So we know what t2 and t1 will be represented as. They are a plus h minus a. But I don't have a representation yet for y2 and y1. So let's start with y1. y1 is going to be equal to d of a. So I take the time 1 value, which is a, t1 value of a, substitute it into d, and I'm going to end up with 16 a squared, which is just the same as saying 16a squared. So really nothing to do there in terms of simplifying, since I don't actually know the value of a. It's an unknown. y2 will be done in a similar fashion. y2 is going to be the distance that goes with a plus h, or t2. So 16 times a plus h squared, and I have to first do the squaring part. That's going to be a squared plus 2ah plus h squared. Then I'll distribute to get 16a squared plus 32ah plus 16h squared. So now I want to substitute in for y2 and y1. y2 is what we just wrote down. So let me copy that. And then y1 was 16a squared. So all of that is divided by the a plus h minus a. Now, with this average rate of change calculation that we're doing, we're going to see that we have a subtraction in the numerator and a subtraction in the denominator. And if you look closely enough, in the numerator, you're going to see that 16a squared shows up in both of those groups. And that means with subtraction, we can just cancel them out. And the same thing occurs in the denominator with a. A minus a is going to end up canceling out. So this statement for the average rate of change, which starts off, looking a little messy here because we have all these a's and h's floating around, is actually not going to be as bad as it first seemed. It's going to be 32ah plus 16h squared, all divided by h. And now we can do this step further. If you look at the numerator, there's a common factor of h there. So this is going to say h times 32a plus 16h all divided by h. So once you factor out the h, then you will have the ability to cancel that out across your quotient. So that's interesting here. We have a set of cancellation that occurs because of the difference, and now we have a cancellation that happens because of the quotient. Hence where we're going with this part of the section called the difference quotient. So ultimately, once we get this simplified, we're going to have 32a plus 16h, provided that h is not equal to 0. And that ends up being the final result here for the average rate of change calculation between t equals a and t equals a plus h. Now, before I finish this video, I would like to take the time to make a good connection with this and example 7.2. So in example 7.2, we had t1 was equal to 1 and t2 was equal to 5. And the average rate of change calculation that we came up with was 96. For example 7.3, we have t1 is a, t2 is equal to a plus h, and the average rate of change calculation is 32a plus 16h, provided that h is not 0. So I wonder if it would be possible, since I'm using the same function, I'm using the same d of t equals 16t squared, could I somehow use the result from 7.3 to confirm the result for 7.2? Because what I was claiming is that the difference quotient is going to be a generalization of the average rate of change. So I should be able to get the same result if I choose the correct values. So here's what I mean by that. If I look at t1 equaling 1 and t1 equaling a, that would imply that I need to let a be equal to 1 in order for these two examples to actually correlate to each other. And then if I wanted t2 being 5 to correlate to t2 being a plus h, then the only way I can make that happen is if I let h be equal to 4, because then 1 plus 4 would give me 5. So it is possible to pick a and h so that way it ends up matching t1 being 1 and t2 being 5. So now I want to take these values of a and h and I want to substitute them into the AROC calculation from example 7.3. So this will be 32 times 1 plus 16 times 4. That's going to be 32 plus 64, which ends up giving us 96, which is exactly what we calculated for example 7.2.